Astronomers didn't aim some of the world's most sensitive radio telescopes at 3I/Atlas to look for aliens. They did it because something was wrong. Not dramatic, not explosive, just wrong. If the latest tracking data is correct, then one of our most reliable models for how these objects behave after leaving the sun is quietly failing. And that's why scientists aren't excited about 3I/Atlas. They're nervous, because this object did what it wasn't supposed to do, and it kept doing it long after the moment when everything should have calmed down. Before we jump to signals, intelligence, or wild theories, we need to slow down, because what the data actually shows is stranger and more uncomfortable than most of the stories being shared right now. Here's the single question that started all of this. Why isn't 3I/Atlas slowing down? That question sounds simple, but in astronomy, it's dangerous. After an object passes its closest point to the sun, the script is usually finished. Solar heating drops, surface activity fades, gravity takes over, velocity decreases. Thousands of comets have followed that pattern. 3I/Atlas didn't. Weeks after perihelion, tracking data kept showing the same anomaly. First, it looked like noise, measurement uncertainty, something that would smooth out with better calibration. Didn't. Once the data was cleaned, corrected, and rechecked, the conclusion became unavoidable. 3I/Atlas was still accelerating. Not dramatically, not violently, quietly, and quiet acceleration is the hardest kind to explain. At first, scientists weren't worried. There was an obvious explanation: outgassing. As ice warms, gas escapes. Gas creates thrust. Thrust creates acceleration. End of story. For a moment, it looked like the case was closed. Except the numbers refused to cooperate. Outgassing doesn't behave like this. It fades quickly. It fluctuates. Jets wander as the object rotates. Thrust vectors change. Acceleration becomes chaotic. But 3I/Atlas didn't show chaos. It showed consistency. And that's when the situation changed. Because consistent acceleration after solar departure isn't just unusual. It's structurally informative. It tells you something about the object's interior, not just its surface. So astronomers asked the next logical question. If something physical is still happening, what trace should it leave behind? The answer wasn't signals. It was emissions. Energetic processes, ionized gas, charged particles, interactions with radiation. All of them leave faint radio fingerprints. Not messages, not patterns, just background noise that behaves in predictable ways. So teams aimed powerful radio telescopes at 3I/Atlas, not expecting a discovery, expecting confirmation. When the data came back, the first reaction was relief. There was no narrowband signal, no repeating structure, no artificial pattern, nothing that suggested intelligence. For a moment, it felt like the boring explanation had won. Then scientists looked closer, because while there was nothing extraordinary in the radio data, there was also nothing that solved the problem. The emissions didn't match the decay curve expected from exhausted surface volatiles. The energy profile lingered longer than models predicted. The behavior wasn't loud, but it was persistent. And persistence is the enemy of simple explanations. This is where the scientific community quietly split. One group argues this is still explainable, but only if 3I/Atlas isn't built the way we assume. If instead of a porous, fragile nucleus, it contains deeper volatile reservoirs. Materials like carbon monoxide or molecular nitrogen can sublimate at much lower temperatures, continuing to produce thrust far from the sun. This explanation is dull, and that's exactly why many scientists like it. But another group isn't convinced. They point out something uncomfortable. Even deep volatile models predict instability. Jets should drift, rotation should change, acceleration should wobble. But 3I/Atlas doesn't wobble much. It holds direction, not perfectly but coherently, and coherence changes the conversation. Because coherence doesn't mean intelligence, but it does mean structure, geometry, internal organization that channels energy instead of letting it bleed away randomly. At this point, the question stops being what's pushing it. It becomes what kind of object behaves like this. And that's when quiet comparisons begin. Not in press releases, not in headlines, but in internal discussions. Oumuamua, that name still makes scientists uncomfortable, not because of aliens but because it broke assumptions. It accelerated without a visible coma. It reflected light strangely, It didn't fit clean categories. 3I/Atlas isn't the same. It has a coma. It looks more comet-like, but the discomfort feels familiar, an object that refuses to decay on schedule. And that's why the radio data matters. Not because it found something shocking, but because it failed to close the case. Whatever is happening isn't violent. It isn't broadcasting. It isn't chaotic. It's efficient. And efficiency is rare in natural systems. Another explanation being debated is internal asymmetry. If the object's mass distribution is uneven, not just on the surface but deep inside, then even weak jets could generate stable thrust vectors. That would require a level of cohesion we don't usually associate with comets, which leads to a quieter, more unsettling possibility. Maybe 3I/Atlas isn't a comet in the traditional sense at all. Maybe it's transitional, an object formed under conditions we don't see here. Remember, this object didn't grow up in our solar system. It wasn't baked by repeated passes around the sun. It didn't slowly lose its volatiles over billions of years. It arrived fresh, and fresh objects behave differently. They don't follow tired rules. But here's the part that really matters. If this acceleration continues, even subtly, it compounds. Small deviations grow, predictions drift, tracking becomes harder, and eventually the precision needed to understand its structure disappears. The window is closing. That's why scientists aren't arguing loudly yet. They're waiting. The next datasets matter more than the last. If the acceleration fades, the boring explanations win. Models adjust. The story ends quietly. But if it doesn't, if it holds steady or increases, then this isn't a measurement error. It's a category problem. Not alien, not artificial, but unfamiliar. And unfamiliar objects are the ones that rewrite textbooks. So ignore headlines about secrets or lies. The real story is slower and more interesting. An object from another star system is passing through ours. It isn't doing anything dramatic. It's just refusing to behave the way it's supposed to. And sometimes, that's all it takes to remind us how much we still don't understand about what's moving through the dark. The next update won't come with an announcement. It will come as another number, another slight deviation. And whether that number bends back toward expectation or keeps going will tell us what 3I/Atlas really is.